The concept of the finitude of the universe as we know it is an idea that has been contemplated by astronomers, physicists, and philosophers alike. It relates directly to a theoretical model of the universe's end known as the heat death. This notion, as ominous as it sounds, is one that is firmly rooted in the principles of thermodynamics and quantum physics. The heat death of the universe is a potential scenario in which the universe, over an astronomical timeline, reaches a state of maximum entropy. In layman's terms, it is a point where all the energy in the universe will be evenly distributed and no more work can be done. This is a direct consequence of the second law of thermodynamics, which states that the entropy or disorder of an isolated system always increases over time. This law is quite evident in our everyday lives. The mixing of cream into coffee, the melting of an ice cube, the rusting of iron, all these processes increase the entropy of the system and are all irreversible. They point towards a direction of time from past to future, and this direction is towards increasing entropy. In the context of the universe, the second law implies that all the stars will eventually burn out, all matter will decay, and all the energy will be used up. Everything will reach the same temperature, a very low one, near absolute zero, and no further change or action will be possible. This is the bleak scenario of the heat death. But when is this supposed to happen? The timeline is mind-bogglingly vast. Estimates range from 100 billion to a Google, one followed by 100 zeros, years into the future. This is far longer than the current age of the universe, which is around 13.8 billion years. It's a timeline so vast that it's hard to comprehend or imagine. The heat death of the universe is not a certainty, but a possibility. There are other models of the universe's end, like the Big Crunch or the Big Rip. However, current observations of the accelerating expansion of the universe seem to favor the heat death scenario. The concept of the universe's end, whether it's by heat death or some other means, raises profound questions about the nature of existence, the purpose of life, and the meaning of time. It also prompts us to contemplate our place in the cosmos and the fleeting nature of everything we hold dear. Despite its grim prognosis, the theory of heat death is a testament to the power of human curiosity and our relentless quest to understand the universe, no matter how vast, complex, or daunting it may be. It's a sobering reminder of the impermanence of all things, even the universe itself. It also underscores the preciousness of the here and now, the only moment we truly have. In the mid-19th century, the concept of entropy was introduced by Rudolf Clausius, a German physicist, as part of the second law of thermodynamics, setting the theoretical groundwork for the heat-death theory. Clausius posited that the total entropy or disorder of an isolated system can only increase over time. Just a few decades later, the British physicist Lord Kelvin extrapolated Clausius's idea to the entire universe. He suggested that the universe would eventually reach a state of maximum entropy, where all energy would be evenly distributed and no work could be done. This was the first reference to a possible heat death of the universe. The concept was further refined in the 20th century with the advent of the Big Bang theory. The Big Bang model was bolstered by Edwin Hubble's discovery of the expanding universe in 1929. The notion that the universe had a beginning implied it could also have an end. This led to a variety of end-of-the-universe scenarios, including the heat death. The theory took on a more concrete form with the discovery of cosmic microwave background radiation in the 1960s. This radiation is the afterglow of the Big Bang, and its uniform temperature across the universe suggested a future in which all energy is evenly distributed, a key feature of the heat death scenario. In the late 20th and early 21st centuries, observations of distant supernovae made it apparent that not only is the universe expanding, but this expansion is accelerating. This discovery, which earned a Nobel Prize in Physics in 2011, has significant implications for the fate of the universe. Current understanding of the laws of physics suggests that, as the universe expands, it will become increasingly dilute and cold. The stars will exhaust their nuclear fuel and die, galaxies will drift apart, and eventually, even the atoms themselves will decay. All the energy will be used up, leaving a cold, dark, and lifeless universe. This is the heat death scenario in its most modern form. Yet, despite the mounting evidence supporting the heat-death theory, it remains just that, a theory. Other potential end-of-the-universe scenarios continue to be explored, and new discoveries could reshape our understanding of the universe's fate. The mystery of how and when it will all end remains one of the most profound and compelling questions in cosmology. Our journey into the past and the future of the universe is a testament to the human spirit, a relentless pursuit of knowledge and understanding, no matter how daunting or disturbing the answers may be. It is a journey that underscores our place in the cosmos and the fleeting nature of existence itself. In the face of such vast and profound mysteries, we are reminded of our own mortality and the preciousness of the here and now. From the earliest days of human civilization, we have looked up at the stars and wondered about the nature of the universe. In many ancient cultures, the end of the universe was often tied to their mythologies and religious beliefs, conceived as cyclical events, great cataclysms, or divine judgment. For instance, in Norse mythology, the end of the universe, or Ragnarok, is a great battle resulting in the death of major figures, the engulfment of the world in water, and its subsequent rebirth. Similarly, Hindu cosmology describes a cyclical universe that undergoes regular creation, destruction, and reincarnation. The scientific understanding of the universe's fate, however, began with the advent of modern astronomy and physics. In the late 18th and early 19th centuries, the French mathematician Pierre-Simon Laplace and the English scientist Lord Kelvin were among the first to propose scientific theories for the end of the universe. Laplace theorized a concept he called the heat-death of the universe. He proposed that if the universe contained a finite amount of energy, and if this energy was constantly being converted into heat and never lost, then, eventually, the universe would reach a state of equilibrium. In this state, all energy would be uniformly distributed, and no work could be done, resulting in a heat death. Around the same time, Lord Kelvin proposed a similar theory. He suggested that if the universe followed the second law of thermodynamics, it would inevitably reach a state of maximum entropy, or disorder, where all heat is evenly distributed and no energy transformations are possible. In the 20th century, Albert Einstein's theory of general relativity revolutionized our understanding of the universe. It suggested that the universe is not static, but either expanding or contracting. This led to the first cosmological models predicting the end of the universe. The Big Bang theory, first proposed in the 1920s, introduced the concept that the universe began from a hot, dense state and has been expanding ever since. This theory, combined with the discovery of the cosmic microwave background radiation and the observation that galaxies are moving away from us, supported the idea of an expanding universe and set the stage for theories of its ultimate fate. Despite these advancements, the question of how and when the universe will end remains one of the great unsolved mysteries of cosmology. Today, scientists continue to test and refine their theories, using cutting-edge technology and observations from space to delve deeper into the universe's past, present, and future. As we journey forward in our quest for knowledge, we continue to grapple with questions that have intrigued and perplexed humanity for thousands of years. The work of cosmologist Stephen Hawking remains integral to our understanding of the universe's end. Hawking, known for his groundbreaking research on black holes and the nature of the universe, contributed significantly to the study of cosmology. His research led to the theory known as Hawking radiation, which suggests that black holes can slowly lose energy and shrink over time due to quantum effects near the event horizon. This discovery is a key piece of our understanding of the universe's fate, as the eventual evaporation of black holes could play a role in the universe's slow march towards heat death. Hawking's contemporary physicist Roger Penrose also made crucial contributions. Penrose proposed the concept of a cyclical universe, where the end of one universe triggers the beginning of another. His model, known as conformal cyclic cosmology, suggests that the universe endlessly repeats a cycle of big bangs and heat deaths. Though the theory has its critics, it represents a radical departure from the conventional view of the universe's one-time beginning and end. Meanwhile, the work of dark energy researchers like Saul Perlmutter, Brian Schmidt, and Adam Rees has shed light on the universe's ultimate fate. Their discovery of the universe's accelerating expansion, for which they won a Nobel Prize in 2011, introduced a new factor into end-of-the-universe theories. If the universe continues to expand at an increasing rate due to dark energy, it may eventually experience a Big Rip, where galaxies, stars, and even atoms are torn apart by the expanding universe. Additionally, the work of physicists like Sean Carroll and Jennifer Chen has expanded on the concept of the heat death of the universe. They've proposed the idea of quantum fluctuations causing a new Big Bang in an infinitely old universe, suggesting a possible escape from the seemingly inevitable heat death. These visionaries, alongside countless others, have shaped our understanding of the universe's potential fates. Their theories, from heat death to the Big Rip, from Hawking radiation to conformal cyclic cosmology, illuminate our exploration of the cosmos, each adding a new layer of complexity to our understanding. As we delve deeper into these mysteries, we find not only answers but more questions, each leading us further into the enigma of the universe's ultimate destiny. As we continue to explore the fascinating field of cosmology, we encounter unexplained anomalies and phenomena that challenge our established notions of the universe's fate. These cosmic irregularities, while puzzling, lend a sense of awe and intrigue to our quest for understanding. One such anomaly is the so-called axis of evil, a term coined by cosmologist João Magejo to describe an unusual alignment in the cosmic microwave background, CMB. The CMB is the afterglow of the Big Bang, and its uniformity across the sky is one of the key pieces of evidence for the Big Bang theory. However, the axis of evil refers to a mysterious pattern in the CMB that appears to align with the plane of our solar system, a highly unlikely coincidence that defies the principle of isotropy, which posits that the universe appears the same in all directions. Another significant anomaly is the Great Attractor, a gravitational anomaly in intergalactic space that's pulling galaxies, including our own Milky Way, towards it. Despite being located tens of thousands of light-years away, the Great Attractor exerts a gravitational force so strong that it's altering the direction and speed of our galaxy. Yet, what exactly the Great Attractor is remains a mystery, as its gravitational influence is far greater than can be accounted for by observable matter alone. Then there's dark flow, yet another unexplained cosmic phenomenon. Discovered by astronomers studying the CMB, dark flow refers to a peculiar velocity flow of galaxy clusters. These clusters, instead of moving in all directions as expected due to the universe's expansion, are observed to have a peculiar velocity towards a specific part of the sky. This motion, not predicted by the standard cosmological models, suggests the presence of a structure or an influence beyond the observable universe, challenging our understanding of its overall scale and composition. There's also the perplexing issue of dark matter and dark energy, the invisible and unidentifiable forms of matter and energy that are believed to make up a staggering 95% of the universe. Despite extensive research, their nature remains a tantalizing enigma, adding a layer of mystery to our understanding of the universe's fate. These mysteries, puzzling as they may be, are not roadblocks but signposts, inviting us to push the boundaries of our knowledge. They remind us that the universe is far more complex and enigmatic than we can currently comprehend, and our journey towards understanding its ultimate fate is far from over. Each anomaly, each unexplained phenomenon, adds a new dimension to this cosmic puzzle, deepening the mystery and fueling our curiosity. It is within these enigmas that we may find the keys to unlock the secrets of the universe's destiny. Despite the predominant view of the heat-death scenario, other theories also exist that contend with this picture of the universe's end. One such idea, known as the Big Rip, suggests that the expansion of the universe, driven by dark energy, could become so strong that it eventually tears apart everything within the universe. This includes galaxies, stars, planets, and even atoms themselves, resulting in a universe that is essentially ripped apart at its seams. In contrast, the Big Crunch theory posits an entirely different fate. It suggests that the expansion of the universe will eventually slow down and reverse due to gravity, causing all matter and energy to collapse back into a singularity, much like the one that birthed the universe in the Big Bang. This could potentially lead to a new universe being born in a cyclic process of expansion and contraction, a concept often referred to as the oscillating universe theory. Then there's the concept of vacuum decay. In this scenario, a quantum event triggers a shift in the universe's energy state, creating a bubble of true vacuum that expands at the speed of light, obliterating everything in its path and resetting the universe to a new, lower energy state. The result would be a universe fundamentally different from our own, with different physical laws and no room for structures like galaxies, stars, or life as we know it. While these theories are all intriguing, none can be definitively proven or disproven yet, as they involve phenomena beyond our current understanding and technological capabilities. They also raise fascinating philosophical questions about the nature of existence and reality. If the universe is cyclical, does time itself loop, and are we destined to experience the same events over and over again? If the universe is ripped apart or decays to a lower energy state, what does that mean for the concept of reality and our place within it? Moreover, these theories remind us that we are tiny observers in a vast, complex universe. Our understanding of it is limited by our perspective and the extent of our scientific knowledge. The universe's ultimate fate, whether it be heat death, a big rip, a big crunch, or vacuum decay, may be completely different from what we currently envision. The universe, with all its enigmas and anomalies, is a cosmic mystery, ever unfolding, ever challenging our perceptions and beliefs, and continually pushing us to question, explore, and seek understanding in the face of the great unknown. In the face of such cosmic mysteries, our minds naturally turn to the ancient civilizations that peered up at the heavens and crafted their own interpretations of these celestial enigmas. Through myth, symbolism, and sacred cosmology, they sought to understand the vast cosmos and their place within it. The Mayans, for instance, believed in a cyclical universe, a concept that echoes modern theories of an oscillating universe. They viewed time as a series of world ages, each ending in a cataclysm and giving birth to a new age. This resonates with modern theories of a cyclical universe, one that expands and contracts in never-ending cycles. Egyptian mythology presents a version of the Big Rip theory. The ancient Egyptians believed that the god Geb, the earth, and Nut, the sky, were once so closely intertwined that nothing could exist between them. It took the intervention of the air god Shu, who held Nut above him and placed Geb beneath his feet, to create space for the universe to exist. In Hindu cosmology, we find echoes of the heat-death scenario. The Hindus envisage a cosmic cycle of creation, preservation, and dissolution. In the final stage, pralaya, the universe is dissolved and all forms of life cease to exist. This dissolution is followed by a period of cosmic rest, akin to the state of maximum entropy in the heat-death scenario, before a new cycle of creation begins. The ancient Norse, too, had a vision of cosmic destruction in the form of Ragnarok. This apocalyptic event involved the death of major gods, the world being submerged in water, and the earth rendered barren, with all life extinguished. This can be seen as a mythic reflection of the universe's potential fate via vacuum decay, where a shift in the universe's energy state could lead to a cataclysmic change in the fundamental laws of physics, extinguishing life as we know it. These ancient myths and cosmologies, though born of a time before the advent of modern science, resonate with contemporary theories about the universe's end. They offer a humbling reminder that our ancestors, too, grappled with these existential questions. While our methods of exploration have evolved, the mysteries of the universe remain as profound and as elusive as ever, continuing to stir the human imagination and drive our quest for understanding. With the rise of modern technology and ongoing research, our understanding of the universe's potential demise continues to advance. Telescopes, satellites, and space missions have become our eyes and ears in the cosmos, probing the enigmas of the universe, unveiling layers of its hidden order, and bringing us closer to understanding its potential end states. Observatories around the world and in space, like the Hubble Space Telescope, have been instrumental in studying distant galaxies, cosmic microwave background radiation, and large-scale structures of the universe. These tools help us detect and analyze the cosmic redshift that indicates the universe's constant expansion. The information we glean from these observations forms the basis of our understanding of the universe's current state, and by extension, its potential fate. Satellites, such as the Planck satellite, have provided us with detailed maps of the cosmic microwave background radiation. This radiation is a remnant of the Big Bang, the echo of the universe's birth. Its uniform distribution across the universe underpins the theory of a homogeneously expanding universe, which is central to the concept of heat death. More recently, missions like the James Webb Space Telescope are set to delve deeper into the mysteries of the universe. This mission aims to observe some of the most distant objects in the universe, study the formation of stars and galaxies, and investigate the nature of dark matter and dark energy. These observations could provide key insights into the universe's rate of expansion and its ultimate fate. In addition to these observational tools, advanced computer simulations allow scientists to model the universe's evolution over billions of years. By tweaking parameters like the amount of dark energy, scientists can predict different end scenarios for the universe. These simulations have been vital in corroborating theoretical predictions about the universe's end, including the heat death scenario. However, despite these technological advancements and ongoing research, the universe's end remains a topic of much debate and speculation. Yet, the continued exploration of the cosmos, the relentless quest for knowledge, and the development of ever more sophisticated tools and theories keep us moving forward in our understanding. The mysteries of the universe, so profound and elusive, continue to challenge and inspire us, pushing the boundaries of our knowledge and our place within this unfathomably vast cosmic theater. The implications of a universe destined for heat death are profound, not just scientifically, but philosophically and existentially. If the universe's fate is indeed a slow, inexorable slide into equilibrium and entropy, what does that mean for us, for consciousness, and for the very concept of life? This potential future paints a bleak picture, but it also underscores the preciousness of the here and now, highlighting the unique and transient nature of existence. It invites us to view life as a brief spark in the cosmic expanse, a fleeting moment of complexity and order in an otherwise chaotic and dissipating universe. In the face of such vast, impersonal cosmic processes, one might question the significance of individual lives, of human endeavors, of consciousness itself. Yet, it is perhaps in this very insignificance that we find our most profound meaning. After all, it is through our conscious experience that the universe comes to know itself, however temporarily. We are the universe made aware, a small but crucial part of its grand narrative. The anticipation of the universe's heat death also challenges our conceptions of time. In human terms, the concept of an eternal, unchanging future seems paradoxical, almost unimaginable. Yet, this is exactly what the heat death scenario presents us with, a future in which time, in a sense, ceases to have meaning. This forces us to confront our understanding of time, to question its linearity, and to recognize its relativity. Furthermore, these revelations encourage us to ponder the mystery of creation itself. If the universe will ultimately meet a cold, entropic end, it begs the question of its fiery, ordered beginning. How did such complexity and order arise from the quantum fluctuations of the early universe? And if it happened once, could it not happen again in some distant, post-heat death future? In essence, the heat death scenario compels us to rethink our place in the cosmos. It urges us to appreciate the fleeting, precious nature of life, to marvel at the existence of consciousness, and to grapple with the paradoxes of time and creation. Far from rendering our lives meaningless, the prospect of an eventual heat death can serve as a powerful reminder of our unique, transient role in the cosmic drama and the profound mystery and wonder that is our universe. In the grand scheme of cosmic time, we are but brief, dazzling flashes of consciousness, capable of wondering, questioning, and seeking answers in the vast cosmic tapestry. The heat death of the universe, the seemingly inevitable end of all things, does not diminish the value of our existence, but rather emphasizes the precious, ephemeral nature of life. We can look upon the cosmos not with despair, but with awe and curiosity. We marvel at its mysteries, its intricate patterns, and its vastness. We wonder about its past, its present, and its future. We contemplate the seemingly insurmountable paradoxes, the questions that seem to have no answers, and the truths that lie just beyond our reach. The heat-death scenario, while bleak, serves as a poignant reminder of the fact that every moment, every breath, every heartbeat, every thought is a miracle of existence in a universe that is slowly marching towards entropy. It is a testament to the transient nature of all things, a call to appreciate the now, to revel in the beauty and mystery of existence, and to make every fleeting moment count. The limits of human knowledge are vast, yet we continue to push these boundaries, driven by an insatiable thirst for understanding. We peer into the cosmos with our telescopes, we delve into the quantum realm with our equations, and we explore the mysteries of consciousness with our thoughts. We strive to uncover the truth, to make sense of the incomprehensible, to find meaning in the seemingly meaningless. The eternal quest for knowledge, the relentless pursuit of truth, the burning desire to understand, these are the hallmarks of our species. They are the driving forces behind our existence, the essence of our being. They are our response to the cosmic drama, our way of grappling with the vastness of the universe and the inevitability of its heat-death. As we gaze upon the stars, as we ponder the mysteries of the cosmos, we are reminded of our smallness, our fleeting existence, and our profound insignificance in the grand cosmic narrative. Yet, it is precisely in this recognition that we find our greatest strength, our deepest purpose, and our most profound meaning. It is in this vast cosmic arena that we find our place, our role, and our destiny. In the grand cosmic drama, we are both spectators and actors, observers and participants. We are the universe contemplating itself, a tiny fragment of consciousness striving to understand the whole. We are the universe made aware, a brief spark in the darkness of space, a fleeting moment of complexity and order in a universe slowly marching towards heat-death. The truth may lie beyond the stars, but it is within our reach. It is within us. The universe is in us. We are the universe. And in this realization, we find our greatest awe, our deepest wonder, and our most profound insight. Thanks for listening. This has been Mysteries of the Universe. If you enjoyed today's episode, be sure to follow us wherever you listen to podcasts. And if you'd like to support the show, subscribe to the Forbidden Knowledge Network on Patreon. Subscribe now.